Today we're going to talk a little bit more about bipolar junction transistors. We talked a little bit about them last time, and we looked at their characteristics. Today we're going to talk about them and see how we can actually use them in some real circuits. So we're going to start off with a review of transistors, and then we're going to do a lecture, and we're going to talk about using transistors in two different ways. First of all, we're going to talk about using them in transistor driver circuits. In this way of using transistors, we use them like on-off switches. They're either fully on or fully off, just sort of binary devices, one or the other. We'll talk about why we use circuits like that, and then we'll talk about how they work, how we can construct them. The second way that we can use transistors is in an analog range. Okay? This is sort of the shades of gray. It's not just 1 or 0, on or off. It's everywhere in between. And those transistors are especially good in the analog range when we are dealing with amplifiers, whether it's audio amplifiers or radio frequency amplifiers, things like that. We're actually going to build some our first type of amplifier in the next class. So today we're just going to start looking at how we can use transistors in the analog range, and that'll prepare us for next time when we actually build an amplifier. Okay? So, any questions before we get started? Okay. Cool. So let's start off with a quick review. So last time we looked at transistors, and we did some measurements, right? We measured the DC gain, right? Anybody remember what that was called? It was yeah, HFE, and the F and E were uppercase. So this was DC gain. Do you remember sort of the range that we found for the DC gain? Yeah, somewhere around 100 to 200 generally. And it was not real specific, right? It was kind of in that ballpark. Sometimes it was a little lower, sometimes it was a little higher, but it was somewhere around there. So we measured that. We looked up the data sheet, and we checked the range for that, and then we actually measured it using the multimeter, right? And we used the multimeter to do some other measurements and other checks of our transistors, right? Remember when we looked at the inside of a transistor, we said that it was made of 3 pieces of silicon sandwiched together. And so those 3 pieces of silicon acting together behaved like 2 diodes back to back. So we said that the transistor acted kind of like 2 diodes back to back. So we used our multimeter, and we measured between here and here, and we checked to see that the diode was forward biased in one direction and reverse biased in the other direction. We did the same thing down here, and then we also measured between these 2 points, and we found that there was always an open circuit, an overload between those 2 points, because one diode or the other would always be reverse biased, right? Do you guys remember what we called each one of these terminals? What about
base?
Yes. This was the base. And then these 2.
Collector, emitter.
Yeah, one was collector and the other one was the emitter. So we'll say this is the collector. And And this one down here is the emitter. If we were to draw the symbol for the transistor, it looks like this. We talked about two different varieties of bipolar junction transistor last time. Do you remember what those varieties were?
NPN, PNP?
Yeah, NPN and PNP, exactly. And which kind did I draw on the board here? NPN, right. That's right. I remember it because the arrow never points inwards, NPN. So the arrow is pointing out, it's an NPN transistor. If we were to draw the PNP symbol for that, looks like this. Again, this is the base, collector, and emitter for a PNP transistor. Okay? So the little arrow is always on the emitter, and the base is the terminal that's connected to the flat part of the symbol, and then the collector is the terminal that's left over. Any questions about that? Okay, cool. So the gain, this DC gain, that related the amount of current that went into the base to the amount of current that came out between the collector and the emitter, right? So if we had a gain of 100 and we had 1 milliamp flowing into the base and out through the collector, how much current, out through the emitter, how much current could we have flowing from the collector out through the emitter? What was it?
100 milliamps.
Yeah, this could be 100 milliamps, right? That's what the gain means. So the gain means that a gain of 100 means that we can have 100 times more current flowing from the collector to the emitter than we have flowing between the base and the emitter. So this gain really allows us to use a very small current to control a much larger current. And this was useful for controlling things like big lights or robot arms or motors or things like that that required more current, and controlling those things with just a small amount of current like you might get from a microcontroller or a small sensor or something like that. Any questions about that? Okay, so that's a brief review of transistors and what they are. So tonight we're going to talk about a couple of different circuits that use transistors. Okay? So the first type of circuit that we're going to talk about is a transistor driver circuit. Like I said, this is a circuit that allows you to either turn it all the way on or turn it all the way off. So it's kind of like an on-off switch. You could think of it as an electrically controlled on-off switch. So you might ask, why do we care? Why would we want an electrically controlled on-off switch? Well, it's for controlling big things with small current, like I said before. So you might want to turn a big light on and off, say. Maybe you want to do that based on a program that you have running in a microcontroller. Well, the microcontroller is not going to have anywhere near enough current to power a big light like you have overhead. So you need to have something in between. You can use a transistor in this case. You can turn the transistor on with the small amount of current from the microcontroller, and then the transistor can control the large amount of current that it takes to power a light, or a motor, or whatever you want. You know, just something that needs a large amount of current that you want to be able to turn on and off. You might want to have a little remote control car and make it either run or stop. You could do the same sort of thing. You could use a transistor for that as well. So that's what transistor driver circuits are. That's why we care. So let's see how they work. So let's say that you wanted to power a little LED. And you have a 5-volt power supply, and you know that you want to have 20 milliamps going to that LED. So you might ask, well, the first thing that you would do is you would actually construct a circuit that involved a resistor that allowed you to have 20 milliamps going to that LED. So how could we choose a resistor that would allow us to have 20 milliamps going to this LED? We'd have to do some calculations, right? So let's do that. So first of all, we'd have to look at the voltage drop across the LED. So anybody remember about how many volts we have across an LED when it's turned on?
0.7.
Well, that's for a regular diode. We have about 0.7. Remember, the LEDs have more, though.
1.1.
Yeah, about 1.5 volts. So that means that we have about 3.5 volts left over, right? So we need to choose a resistor here that will have 20 milliamps flowing through it when we have 3.5 volts across it, right? So what law could we use to figure out that resistor? Ohm's law, yeah. You say Ohm's law is written like this, and we're trying to figure out the resistance, right? Yeah, so we cover that up. We see it's V over I. So in this case, what's our voltage? 3.5 volts. And what is the current that we want? 20 milliamps. So what is 3.5 volts over 0.02 amps?
1.75 K.
Okay, so 1.75.
No, that's not right.
No, it's
175 ohms.
175 ohms.
175 ohms. That seems a little bit low. No, I guess that's about right. Okay, so 175 ohms. All right, so cool. So the first thing that we would do if we were trying to power this LED is we would build a circuit that looks like this. And we know that when we hook up this circuit, we'll get 20 milliamps flowing through that LED, right? Yes.
Why 20?
if you look at the data sheet for a lot of LEDs, 20 milliamps is sort of right in the middle of the range of what is acceptable. So you could have a little more and it'll be a little brighter, or a little less, it'll be a little dimmer, but that's a pretty standard value. All right, so we've got this circuit, and then the next thing that we want to do is that we want to insert a transistor so that we can turn the light on and off, right? So what we would do is we would insert a transistor down below. So now, this transistor can control the amount of current flowing through there. So we want to be able to hook this transistor up to our 5-volt supply, and we want to have basically a switch here that we can use to turn the transistor on and off. So can we hook the 5 volts directly to the base of this transistor? Remember, the transistor is kind of like two diodes back to back, right? And so we have a diode going from the base to the emitter. So what would happen if you tried to force 5 volts across a diode? Yeah, it would blow up, right? The diode wants to have at most 0.7 volts across it, right? So if you try to force 5 volts across that diode, it's going to overheat and melt, and your transistor is going to go away. So what we have to do is we have to put a resistor in the way. And now we have to choose this resistor value, and this choice is going to determine how our transistor behaves, right? So we want, when this switch is closed, we want the transistor to be on, completely on, and act pretty much like a wire, right? Have almost no resistance. When the switch is open, we want the transistor to behave like an open circuit, a brick, have essentially infinite resistance. Okay? So we need to choose this resistor in such a way that when the switch is closed, the transistor acts like a wire. It has very little resistance. Okay? So the way that we do that is we use what we know about the gain of this transistor. Okay? So we know that the gain it was somewhere around 100 to 200, right? Something like that. We're not exactly sure what it was, but let's say that it was 100. Okay? So suppose it was a gain of 100, and we wanted to have exactly 20 milliamps flowing through this transistor when we were supplying current. How much current would we need to supply here? Yeah, so about 0.2 milliamps, right? We have 0.2 milliamps going in. We have a gain of 100. That means we have 100 times more current going from the collector to the emitter, right? So 100 times more would be 20 milliamps. Okay. So we know that if we knew that the gain was exactly 100 and we wanted exactly 20 milliamps flowing through there, then we could use 0.2 milliamps going in, and then the circuit would work out exactly right. But we don't know exactly what the gain is, right? So what can we do to sort of fudge this a little bit and allow the circuit to work even though we don't know exactly what the gain is? Yeah, double it, right? Sure. So we know that it would just be working if everything was exactly right when we had 2 milliamps going in. We could just double it, right? We'll put in 4 milliamps. The rest of the circuit is already set up to limit the amount of current to 20 milliamps. So we're never going to have more than that. We're never going to hurt the LED by having too much current because the rest of the circuit is already set up. So we can just put in a little extra current into our base, and then that'll open up our transistor extra wide, if you want to think about that. So it'll sort of completely allow as much current as we possibly need to flow through there, and the rest of the circuit will take care of limiting the current to what we need. Yeah.
I'm assuming the max current is normally spec for the transistor, so you know
yes.
how much more you can put through without blowing it up.
Yes, yes, exactly. So you would want to look at the data sheet for the transistor to make sure that you're within tolerance and within spec. But as long as you're within spec, you can just increase the current to more than your circuit would normally need, and then that'll make sure that the transistor is open extra wide. You know, you can even go wild and triple it, right? I mean, you're talking about 0.6 milliamps. That's a very small amount of current. So the idea is you just give yourself what's called a factor of safety here. So you just use more current here than you actually need, which opens up the transistor extra wide, because you don't want the transistor to be ever limiting the current through this circuit, right? You want the transistor to be to be completely on when it's on, right? And then when we disconnect it, of course, we have no current flowing in. And when we have no current flowing in, it should be completely off. So that's how we can make the transistor either totally on or totally off, like an on-off switch. Okay? Any questions about that? All right. So that's a little bit about transistor drivers, and that's what you're going to do for the first part of your lab. I'll go into more detail when we do the lab preview, but for the first couple of circuits in your lab, you're going to be building a setup kind of like this. I think the first one you build something just like this to make sure that it can go on, and then afterwards you do the same sort of thing, but you have a square wave coming in here. And the square wave causes the transistor to turn on and off, which then turns your light on and off. Okay. Cool. So that's transistor driver circuits. Those again are transistors that act like on-off switches. So next I want to talk a little bit about using transistors in analog circuits. This is sort of the gray, the not fully on and not fully off, somewhere in between. Okay? So when you have a transistor that's not fully on and not fully off, we use those in amplifiers quite a bit. And the basic structure looks something like this. So you've got a supply voltage up here, and you've got your transistor. So again, this is the collector, this is the base, and the emitter. So what we want to do when we have a transistor set up like this is we want to show something called a DC load line. So this is a graph, and the graph shows the amount of current that's flowing through the transistor versus the voltage. Okay, so let me make sure I get the axes right. So this is the amount of current that's flowing through the transistor, and then this is the voltage between the collector and the emitter. Okay? So let's say that this is 5 volts and this is 1 kilo ohm. Okay, just for example. Imagine that I have no voltage between the collector and the emitter. That is to say that the transistor is acting pretty much like a wire. Okay, so it's totally on, like we saw a minute ago. How much current would be flowing through this circuit? Yeah, 5 milliamps, exactly. What happens is that this is just acting like a straight wire, right? So you basically have a circuit with 5 volts on one side and a 1 kilo ohm resistor going to ground. So you can use Ohm's law and you get the current is 5 volts over 1,000 ohms, and that's just 5 milliamps. So that's one point that we can plot on our graph. So we said when we have 0 voltage between the collector and the emitter, we have 5 milliamps flowing through into the collector, right?
So there's no, from the collector to the emitter, there's no voltage drop on the transistor?
That's right. That's right. There's no voltage drop when the transistor is fully on. What about when the transistor is totally off? It's acting like an open circuit. How much current is going to be flowing through there? Right, no current. No current. And how much voltage would we have between the collector and the emitter? Yeah, 5 volts. Right? This is just acting like an open circuit. So there's no current flowing through the resistor, and when there's no current flowing through the resistor, there's no voltage drop across the resistor. So both sides are at the same level. So this side is at 5 volts. The collector must also be at 5 volts. And the emitter is tied directly to ground, so that's at 0 volts. So there's 5 volts between the collector and the emitter when no current is flowing. So that's another point that we can plot on our graph. So at 0 current, we have 5 volts between the collector and the emitter. Now what we could do is we could plot a whole bunch of points in between. So we could start putting a little bit of current in here and just start turning the turning the transistor on just a little bit and measure the voltage between the collector and the emitter, and then slowly increase the current. And what we would see is we could put a whole bunch of more plot points on our graph, and we would see that this is a straight line. I tried to draw a straight line, it had a little dip in it, but this would actually be a straight line between these 2 points. So that means that the middle of this curve, or the middle of this line, would happen right at half of our input voltage, about 2.5 volts, and half of our current. .5 milliamps. So I apologize, my graph is a little bit wonky, but this middle point happens at half of the maximum voltage and half of the maximum current. So this middle point is called the this is the class A bias point. Because when you're using a Class A amplifier, like we'll see next time, you set the transistor to be right at this point. Okay? So, any questions about this type of circuit? All right, so that is how we can use transistors in the analog range. This graph is called the DC load line. Yeah?
When you call it the analog range, you're just referring to the fact that it's either all the way on or all the way out.
That's right. That's right. It's in between being all the way on and all the way off. So if you have the voltage all the way up, then the transistor is off. If you have if you have no voltage between the collector and the emitter, then the transistor is all the way on. Okay. Any questions about that? Okay. So let's do a quick preview of today's lab then. So for the first part of the lab, you're going to be dealing with the transistor driver circuits. So you're going to be building the circuits like I showed you a minute ago, and you're going to turn the transistors all the way on, and you're going to turn them all the way off. You're going to set up the circuit, and you're going to actually measure the beta, which is the gain. You're going to measure that with your meters, and then you're going to use that and calculate how much current you need to have flowing into the base to turn that transistor all the way on. And then you're going to select a resistor that allows you to do that. Okay. For the second part, you're going to do essentially the same thing, but you're going to have the resistor hooked up to a square wave generator, so you can make the light flash on and off. You're going to do the same part of same type of circuit in part 3, but you're going to use a PNP transistor instead of an NPN. And then for the last part of the lab, for part 3, you're going to build a divider bias circuit. So that's going to be essentially like what we have here. The circuit in the lab book has a few extra components. So in the lab book, there's another resistor down here. And you're going to set the current into the base using a voltage divider made up of a single resistor in series with a potentiometer. So you've got a 1 kilo ohm resistor here, and then you've got a 10 kilo ohm potentiometer. So you're going to set up this circuit. You're going to set it up so that you have no current flowing into the base. And then you're going to measure the voltage between the collector and the emitter. And then that's called cutoff. Okay? So when you have no current flowing in, the transistor acts like an open circuit. It cuts off the current between the collector and the emitter, so that's the transistor is said to be in cutoff mode there. Next, you're going to set the current so that you're going to set up the voltage at the base so that the current is entirely free to flow through the transistor, and that's called saturation. So that's when the transistor is entirely on, and you're going to measure the current and the voltage through the transistor there as well, and you're going to plot those 2 points on a graph in your lab book. And then you're going to find this Class A bias point. This is also known as the Q point. And you're going to mark that on your graph. Okay? So that's pretty much everything that I wanted to say about that. Any questions about that? Okay. All right, then you guys can take a 10-minute break or so. Actually, let me take attendance first, and you can take a break and do the lab.